Thank you all for coming. I'm super excited that you're here. And so my name is Stephan. I'm an engineer at Airbnb by day, and by night, I prove theorems in a proof assistant called Coq. So there's a variety of situations in which you might want to engage in such behavior. So let's say you're designing an algorithm and you want to prove that it has certain properties, or maybe you're building a consensus protocol and you want to prove that it makes progress, or maybe a cryptographic protocol and you want to prove that it's secure, or you want to prove that a type system is sound, or you want to prove that a theorem is true in general. So these are all things that I think Coq is pretty good at, and so that's what this talk is going to be about. But before you get started, I want to make it super clear that everyone is welcome to ask questions at any point. For me, it's a lot more important that you understand all the material that we cover, more so than that we cover all the material. So definitely just shout out questions. We're all people, we talk to each other. And before we get super deep, I want to just talk about logic for a moment. So what do mathematicians do? They write proofs. Okay. And a proof can be informal. So you might prove that a suspect is guilty of a crime, or something. I don't know, it's kind of dark. But so in fact, most of the proofs that mathematicians do have a certain sense of informality to them as well. But there's this understanding that with enough effort expended, if we had to, we could elaborate these informal proofs into something formal that could be checked mechanically for correctness. So that's what this is about. So formally, a proof is when you start from axioms and you use inference rules to derive conclusions. And the idea of an inference rule might be a bit foreign to you if you haven't taken a class in logic or philosophy or something like that. So here's an example. This is probably the most well-known example of an inference rule in logic. It's called modus ponens. And it goes like this. If A implies B and A, then I can conclude B. OK, that's in some sense, the whole point of implication is to be destructed by this rule. So it's hard to refute this. I've never met a human being who would look at this and be like, no way, I don't think that's true. So that arrow there means implication, by the way. So just to make it more concrete, let's replace A and B with some propositions that involve me. So here's an example. If Stephan is at LambdaConf, implies that Stephan is in Boulder. And if we know that Stephan is in LambdaConf, then Stephan must be in Boulder also. And if that looks weird to you, it might be because Stephan is kind of a weird name. If you ever have children, I strongly recommend that you give them normal sounding names. Just do them a favor. They will thank you for the rest of their life. And I want to switch gears a little bit and talk about programming. This is a functional programming conference, so we should be talking about programming. And in programming, we often talk about types. Many programming languages have a type system and a type checker. What does a type checker do? So I think we all know the answer on like an informal basis, but a type checker really proves that a program has a specific type, possibly with the help of annotations, by using a set of inference rules in the similar fashion as we do in logic. So here's an example of such a typing rule, is what we call it. So if f is a program that has type A, arrow B, so OK, that means f is a function, right? It takes an input of type A and returns an output of type B. And if we know that x has type A, well, that's convenient because that's exactly what f is hungry for. So the application f of x should give us something of type B. So this is the inference rule for function application. I know that probably a minority of us have actually really implemented a type checker. So this might be a little bit strange, but type checker basically just follows a bunch of rules like this. And here the arrow is the type constructor for function types. Now, I think probably many of you can see where this is going. If we put these rules side by side, so on the right we have the application rule for programming, and on the left we have modus ponens from logic. Now if you squint your eyes a little bit, it sort of looks the same, doesn't it? Not quite the same, because on the right we have f and x and f of x, and Those don't occur on the left side. But there's a way to think about logic. It's called intuitionistic logic, where a proof of an implication, A implies B on the left, can be thought of as a function that takes a proof of A, maps it to a proof of B. So if I give names to those proofs, it looks like this. So here, f is a proof that A implies B. In other words, f is a function that takes a proof of A and maps it to a proof of B. And if x is a proof of A, then I can conclude B via application. So the idea here is that there's this correspondence between modus ponens from logic and function application in programming. So on the left, f of x, those are proofs. And on the right, they're programs. So that sort of like hints towards a correspondence between proofs and programs. I'm sure many of you have heard of this before. And just to give another example of this correspondence, so it's not just functions and modus ponens. Another example is conjunction from logic. So that's just a fancy way of saying and. So if I have a proof P that's A and B, so this shape, this caret thing, just means and, then I can sort of project out the proof of A. I can just get the proof of A. That's what's saying on the left. And I can also get a proof of B. And that intuitively, that makes sense, right? If A and B is true, then A should be true, of course. The same for B. Now on the right, we have the programming world. And here, P is a tuple, like a pair, containing something of type A and something of type B. And of course, I can extract out the A from it, or I can extract out the B from it. And so these rules on the left and the right, they sort of look the same, don't they? Modulo the difference in syntax. So we have parentheses for tuples on the right, and this caret thing for conjunction on the left. But other than that, it's the same rule, isn't it? So there are many other examples. And this whole idea goes by the moniker the Curry-Howard correspondence, or the Curry-Howard isomorphism. The idea is that types in programming, so types correspond to propositions that you might prove in logic. And programs correspond to proofs of those propositions. So anytime you're writing a program, you're really proving a theorem. And anytime you're proving a theorem, you're writing a program. So that's, when you first learn about this, it's one of those like kind of mind-blowing ideas. And the whole rest of the talk is actually going to be about this idea. So any questions so far? Who's heard of this Curry-Howard correspondence? Oh, great.
The words.
Just the words, OK. All right. So let's talk about Coq now. So what's Coq? So Coq is an interactive theorem prover or a proof assistant. It's a piece of software. And it actually has a few different components to it. There's a small core, pure functional programming language called Galena. And if you are familiar, if you know a language in the ML family, like OCaml or Haskell, then I think the syntax will be pretty familiar, I'm hoping. And on top of Galena, there's this other language called LTAC, which is it's more like a scripting language for doing proof automation. So it turns out that writing proofs in Galena by hand is very tedious, as we will see. And the proofs can get long, and you don't want to just write them all out, because it would take forever. So we have this scripting language called LTAC. And there's an important thing going on here, which is that LTAC is one of the most unsafe languages you've ever heard of. It's dynamically typed. There could be bugs in so we call it the script's tactics. Could be bugs in the tactics, but it doesn't matter, actually, because these scripts are actually just generating proof terms, which are then checked in Galena, according to Galena's type checker. So if there's any kind of bug in your proof scripts, then it'll be caught. So you're never going to run into a situation where you prove something that shouldn't be proven, unless, of course, there's a bug in the Galena type checker, or the Galena logic is found to be inconsistent, which hasn't been the case so far.
I have one comment about that name, Galena.
Yeah.
That's a word in Spanish that means hen.
Ah.
So it's cock and hen, which is quite cute.
Does anyone speak French here? Is that right? It means rooster? OK. That's kind of like What's the thing? Apple is like the same word in every, or no, it's pineapple. It's the same word in every language except for English. It's pineapple. Yeah. So I don't know what happens to languages there. But the same thing happened to LTAC. There's a bunch of tactics that are very strange, and I think it's like accident of history. So, all right. So this is what Coq looks like. Well, this is one interface to Coq. So this is called Coq IDE. You can download it from the Coq website right now if you wanted to. This is probably the easiest way to get started with Coq. You just download it, and it's a GUI program. You don't have to configure anything. There's also an Emacs interface. It's called Proof General. So that's a pretty popular one. My lab in grad school used Proof General. And I think there's one for Vim, but I don't use it because the last time I tried, it was buggy. So OK, your mileage may vary. This is a safe bet. So I have a GitHub repo. So it's github.com, which might soon be microsoft.com, I think. But so if you go there, there's all the code I'm about to show you will be in that repo. And it also has some infrastructure to help you get started. Like there's a makefile, so you can just type make in there, and if you have Coq installed, it'll compile the code. Cool. So this is Coq. I'm going to show you some code. And code looks scary. So if we go too fast, I want you to let me know. And I'm going to try to show the equivalent code in Haskell in comments here. So actually, who knows Haskell? Oh, that's almost everyone. OK, great. So in Haskell, if we want to define a data type for Booleans, we'd write this, right? So data bool equals true or false. There are two constructors. It's an algebraic data type. And Haskell also supports a different syntax for defining data types. It's called gadgets, or generalized algebraic data types. So you could define bool like this in Haskell. So with this notation, you give the type signatures, you give the types of all the constructors explicitly. This gives you a little bit more flexibility. And it turns out that the Coq definition of bools will look a lot like that. So here it is. I should explain what the green means. So Coq is a statically typed programming language, but it might be a little bit different than other statically typed programming languages that you might use, in the sense that usually you run the type checker on a whole file at once, or even a whole program. But in Coq, you run it incrementally. So I run the type checker up to this point in the file. And via this whole Curry-Howard idea, type checking is the same as verifying the proofs. So essentially what that means is everything up till this point is accepted by Coq. OK, so Booleans. All right. Just quickly mention the syntax here. So the inductive keyword is how we define a new inductive data type. Inductive data type is a lot like an algebraic data type. It's even more like a generalized algebraic data type, subject to some restrictions. So the main restriction here is that the type that I'm defining, actually, there are a few restrictions. I think I should probably just postpone that until later. But actually, in a sense, inductive data types also generalize algebraic data types because they can be dependent. You can have dependent types. And we'll talk more about dependent types later, but they will become very important for writing proofs. OK, so here's a more interesting inductive data type. So this is a type for natural numbers. A natural number, for our purposes, will be a non-negative integer. And in Haskell, you just write it. You do an ordinary data type. Nat is equal to 0, or a successor of another nat. And we have the same thing in Coq. We have, by the way, I'm repeating definitions that are actually in the Coq standard library. And I'm using the same names to avoid any confusion. So as a result, some of the names might be a little bit strange. But I think it's better this way, that we don't make duplicate names for the same idea. So I'm defining a data type called nat. And so this is interesting. Nat is a set. So what's going on there? So nat is a type. But what's the type of a type? So you might say it's a kind. OK. But in Coq, so there's actually maybe, if we call them kinds, then there's two kinds. There's set and there's prop. And so Yeah, Curry-Howard isomorphism is that proofs and programs are the same thing, but in practice, it helps to separate them. So proofs will roll up into the kind prop, and ordinary data types for programming will be set. And the reason why we do that is because Coq has an extraction mechanism that lets you erase all the proofs and just get a program in Haskell or OCaml. So we probably won't have time to do any of that today, but that's just an explanation of what set is. It's just the kind. OK, so there are two constructors here. O, that's the letter O, but it's meant to look like a 0 because it stands for 0, which is a natural number. And S, which stands for successor, is just another natural number plus 1. That's the intended meaning. So it's a constructor that takes a nat. And then so it's a constructor that takes another nat. Any questions so far?
So all these inductives, this is examples of
Golang? So technically this is the vernacular, which is a third language. So Coq is 3 languages, really. It's Galena, which is the core type theory. And then it's LTAC, which is the language for scripting. And then there's the vernacular, which is like these top-level commands, inductive being one of them, that introduces a new inductive data type. Another example of a vernacular command would be check. So check is like, give me the type of something. And then it prints it over here. So O is a nat. So these like top-level query kind of commands are in the vernacular. But this, you can think of this as syntactic sugar for a Galena term. Oh, by the way, so I didn't explain the pane. So on the left, so you notice there's like split into 3 windows, right? So on the left, this is where I write the proofs and the code. And then in the top right, that's if I'm in the middle of a proof, then it'll show me the proof state, which means that it'll show me the goal I'm trying to prove and the assumptions that I'm allowed to use to prove it. And then the bottom right pane, which I just demonstrated actually. So if I do check O, you can see. So if I like write these vernacular commands, I want to like ask the Coq system for the type of something, or tell me all the lemmas that involve nats that I might be able to use. So those kind of results will show up in the bottom right window. OK. Cool. So so let's check the types of some terms. So O is a nat, S of O, successor of 0 is a nat. Great, these are all nats, so that matches our intuition. Let's talk about functions. So here's a function that takes a bool and flips it. So if it's a true, it becomes a false, and false becomes true. And there's the Haskell definition, but based on my understanding of the audience, I think this is all super trivial to you, so we can speed up. So here's another vernacular command, compute. So one of the weird things about Coq maybe is that you don't usually run the programs, or at least that's not the primary goal here is to just produce a term that type checks. But sometimes you want to run the program, so this is how you do it. You type compute and then a term. So in this case, we're computing neg_b of true, which gives false. Great. And neg_b of false is true. And since you all know Haskell, you understand that function application is just white space. So I type the name of the function, and then I type the argument, and that's the application. All right, so that's a definition. A definition doesn't have to be a function, but this one happens to take an argument. But if I want to make a recursive definition, like say a function that adds 2 natural numbers like this, then I've got to use the fixed point keyword. So Esther's talk right before this session went over the theoretical foundations for fixed points and how you can get recursion from that. But you don't need to know that here. And in fact, it's kind of just like a play on words, really, because fixed points, there's not really like there's no y combinators happening here. It's really just saying that this is a recursive function. And furthermore, it has to be structurally recursive. So it has to be like well-founded. It has to always terminate. You might wonder, how does Coq check that all your programs terminate? Does it solve the halting problem? No, of course not. It actually has a very simple syntactic condition that must be satisfied. In this case, we're doing structural recursion on n? Yes, so n is decreasing at every step until it gets to 0. And Coq can see that pretty easily. If you know about the phrase primitive recursion, then that's essentially what's going on here. Why is it important that terms terminate? Terms terminate. That's kind of a funny sound. So if you could write an infinite loop in Coq, that would be a disaster, because then you could prove any theorem by defining it in terms of itself. So we absolutely have to rule out that possibility. So Coq is very careful to make sure that you can't do that. OK, and just for fun, let's compute 1 plus 1. We get s of 0, which is an ugly way to say 2. OK, so that's the introduction to the core syntax of Coq. So now let's move on to some more interesting stuff. Programming with dependent types. I think Jeremy's here. He talked about dependent types yesterday. But here's an example of a dependent type. So slist is going to be a list of strings. But what's special about this list is that it's indexed by its length. This is actually like the prototypical example of a dependent type, for good reason, because it's very easy to define. So let me just make this a little bit bigger. So it's just an inductive data type, nothing to be afraid of. It's parameterized by a nat. So that's what's going on here. Usually when we define a type, we say its kind is set or prop or something like that. But here, its kind is actually, well, it's parameterized over a nat, right? And there are two constructors. So s_nil, it represents an empty list. And of course, the length of an empty list is 0. So I'm giving the type here of this constructor, which is slist of 0. So that's a dependent type because this is a type, but inside this type, we have a term, one level below. Oh, OK. And then scons is it's like the familiar cons operator on lists, but it's got some extra stuff. So here we're quantifying overall n. And the curly braces here just means that n is going to be an implicit argument, which means that when I invoke this constructor, I'm not going to manually supply n, because usually Coq can figure it out for me. And it's not necessary to specify it manually. So this is going to be the length of the tail, the length of the list that I'm consing onto a new head. And then I take a string as an argument for this constructor. So that's just going to be, it's a list of strings, right? So that's just going to be the head that I'm consing onto the tail. And this is the tail. And notice that the type of the tail is a dependent type. So we have a list of n, so list of length n. And now when I call this constructor, what I get out finally is a list of n plus 1 length. So that's what the s means, plus 1, right? Successor. OK, any questions about that? That's when you first learn about dependent types, this is incredibly confusing, I think. So it's worth spending a moment to stare at it. Cool, no questions. OK, so yeah.
The code, so these checks down there, right? You provide them sample lists.
Mm-hmm.
Can you like run it and see what do they print?
Absolutely,
the
yeah.
Then?
Yeah,
like
so
code computing the length. What are you proving?
I actually haven't done any proofs yet.
Okay.
We'll get to that in the next
cool.
part. Yeah. But let's go through that. It's a great idea. So what's the type of s_nil? It better be a list of length 0. Oh, there it is. OK. And what's the type of, well, if I cons the string foo onto nil, I get a list of length 1. Oh, great. And then I can of course, get a list of length 2 by doing that again. OK. So this is just basic dependent types. And we'll get to proofs just in a moment. But first, we should talk about how do you define functions that operate on dependent types. It can actually get a little bit tricky. So here's a function which concatenates two lists, right? But you see some extra stuff here that's normally not in a typical concat function like you'd see in Haskell. So we have n1 and n2. These are implicit arguments because they're in curly braces, remember? These are going to be the lengths of the two lists that I'm concatenating. So it's like they're the first arguments of this function. And then here I'm taking a list of length n1. So that's what this is saying. The list is called L1, and its type is slist of n1. And then I'm taking another list of length n2. And here's the return type. The return type is a list of length n1 plus n2. So I have a plus inside a type. So that's pretty strange. But that's just dependent types. That's just having programs inside types. That's what it's all about. Is there any confusion about the syntax? So this colon here, it means that it's like a type ascription. So I'm saying that the result is going to be this type. That's all that is. OK, so this dependent pattern matching, that's what's going on here, is worth spending a few minutes exploring because there's some subtleties involved. So this is just pattern matching. So I have recall that the usual way you define concatenation on lists is you recurse on one of the lists, and you take things from that list and put it on the other list. So that's what's happening here. I'm just doing a pattern matching on L1. Now there's this thing in slist n3. What's going on there? So what I'm saying is that the type of L1, well, we already know it, right? It's just slist of n1. So OK, so why do I want to refer? So this, what I'm doing here is I'm referring to the type again. But the difference is that n3 here, so this is a pattern. And n3 is going to take on different values in the different branches of this match statement. So if you're familiar with like this flow-sensitive typing, like that Flow has or TypeScript, it's kind of like a similar idea. Inside the different patterns or inside the different branches, I have different types. So we'll see what I mean by that in a moment. And then this return, so this is another kind of possibly confusing thing. This doesn't mean return like I'm returning a value, and this doesn't mean return like I'm in a monad. This means this is the return type of this expression, of the match expression. So what I'm going to return is a slist of n3 plus n2 length. Now here we can kind of see what's going on with the n3. n3 is the weird part here. n3 takes on the value n1 in this part of the code. And that allows it to unify with the return type of the whole function, right? So if you substitute n3 for n1, then you get n1 plus n2 here. And it type checks, so great. But then n3 inside the branches is going to be different. So in the nil case, n3 takes on the value 0. And in the cons case, oh, you can't really see it. But n3 is the successor of the length of L3. OK, I don't want to dwell on this too much, but this is almost the full syntax for pattern matching. Dependent pattern matching is kind of a complicated topic. And I think still in 2018, it's a little bit poorly understood. So suffice to say, this is how you concatenate two dependently typed lists. Any questions? Actually, yeah. Any questions so far? Yes?
Why didn't you need to do that
for n2? So I'm not destructing n2 at all, right? I'm only doing pattern matching on. Sorry, I'm not doing pattern matching on L2 at all. So there's no in the different branches, like the length of L2 is going to be the same no matter what. All this kind of nonsense is really just I'm just giving types as hints to the type checker. So if it helps to think about this, you can actually just like basically delete this line and then delete this, and then it looks like the familiar Haskell definition, mostly.
Why do you need n3 when you already have n1 up there?
So the reason why is because here n3 is actually a pattern that takes on different values in the different branches, whereas here n1 could be an arbitrary expression. It's not necessarily a variable, which means I can't substitute it away. And that's what I need to do in these two branches. I need to replace n3 with particular values. I wouldn't be able to do that if I had an arbitrary expression there. So basically, n3 kind of like bridges the return type and like the inputs to this match expression. So like here, n3 makes the return type work out for the type checker. But in here, it makes it work out for the recursive call to concat. sometimes it's helpful to like just delete stuff and see what happens. So if you delete this, you run it, we get an error here. OK, N3 is not defined. That's kind of a dumb thing to delete. But what if I delete this?
N1 instead. What you should try to put N1 instead of N3.
Oh, right here?
Yes, right here and below.
So here and here? So it actually works because I'm shadowing the other N1. So this is a little bit misleading, and that's why I called it N3 originally. But here I am still introducing a new variable N1, despite the fact that there's already an N1 in scope.
Can you put an underscore?
So what happens if you get rid of the N?
I mean like this.
No. Keep the N1 from above.
Ah, so keep this one?
No.
Or keep, OK, like that? OK, so.
Oh, we're going to 6 point. Okay, no, sorry. I get it now. Sorry.
I'm glad that helped you, because that did not help me at all. This is an incomprehensible error. All right. Fortunately, in practice, when you write a lot of coq, you don't really have to do this very much. A typical example of when you want to use dependent pattern matching is when you're doing proof by induction. But there's actually a tactic that sets it all up for you. So you rarely have to write these kind of complicated match expressions. All right, so let's talk about logic. So this is the first. Now we're going to start getting into proofs. There's something that happens whenever a student learns about coq for the first time and they see something like this. Inevitably, what happens is they get confused about Booleans, which are just ordinary terms that we use in everyday programming, unless you maybe subscribe to this Boolean blindness thing. And then there's these propositions, so for example, true is a trivial proposition. And what makes it trivial is that there's a constructor here that doesn't take any arguments, which means there's no premises that you have to satisfy. In order to get a proof of true, you've always got one. It's just a constructor that takes no arguments. So what's going on here, maybe I should say a little bit more about this. This is an inductive data type that represents a proposition. Remember that types and propositions have this correspondence, right? So I'm defining a new type, but in a sense, I'm defining a new proposition, which is always true. And it's true because I can construct a proof of it. That proof is trivial, which is a play on words. Now take a look at this one. So here's a proposition which is not provable because there are no constructors. There's no way to get a value of this type. So the dot here just means, OK, I'm done defining the type, and I didn't give any constructors at all. So there's no way to construct a value of type false. All right, so now let's get to some fun logic stuff. So here I'm defining a new proposition or a new type, which is parameterized by two other propositions, P and Q. And in order to construct a value or a proof of this type, I've got to provide a P and I've got to provide a Q. That is a proof of P and a proof of Q. And then what I get back is a proof of and P, Q. I'm defining logical conjunction. That's what's happening here. So I think this is a beautiful thing, because in coq, you just define a whole universe out of thin air. You don't have to these things don't need to be built into the semantics of the language or the typing rules or anything like that. It's just you have basically inductive data types and functions and nothing else. And from that, you can prove essentially all of mathematics. Yeah?
Can you describe why uppercase and lowercase in different contexts? Like and is lowercase, like true and false uppercase?
Yeah, I can describe it. The answer is because I wanted to match the coq standard library, which is horribly inconsistent.
Fair.
Yes?
So would one of the goals be to define a set of axioms as an inductive basis that you would then use to create a proof?
It's a little bit interesting to call those axioms then. OK, that's one interpretation of the word. But so coq also, just to mention this, coq has a keyword called axiom, which allows you to basically say, I have a absurd proof of false. And coq will it'll like warn you, it colors it in yellow, but it allows you to basically assume, oh, I do have a proof of false. So that's really another way to introduce axioms into the system, I suppose. But this way is like you're actually bypassing everything. The type checker. So yeah, I guess it's the way you interpret the word axiom maybe has a different answer depending on how you think of that. I think this will become more clear as we do more examples. So
Where is CONJ? Is that
stands for conjunction.
a primitive of the language?
No.
Define like 17.
It's defined right here. It's just a constructor for this data type.
Oh.
So in the same way that I defined bool, which has true and false, I defined and, which has conj, as its only constructor. These are great questions. I think you should ask more questions. Because so I was in a talk yesterday, a workshop that I think went a bit over a lot of our heads halfway through, and then none of us ever caught up. So like basically the second half of the talk is a little bit sad because we didn't understand a lot of stuff. So that cannot happen here. It's much better that we understand what's going on, even if it means we don't get through the end. Yeah.
Is there an advantage to doing inductive NPQ equals case with cons instead of just define NPQ equals PQ to NPQ, or would that make sense?
Can you say that again?
Could I not just have a definition of NPQ being equal to P to Q to
Something like this. And then I don't know what's it.
and then what? Yeah, there's something to, or you could put the built-in end of stuff.
So I think what my interpretation of what's happening here is we're doing like a church encoding of this data type. So yes, this is totally a valid way to define conjunction, just not the way that standard library chose to do it. Yeah, that's a great question.
Is there a way to do this inductive prop that it won't turn green?
So is the question, is there a way to define an inductive data type which Coq rejects?
Yes.
Yes. Well, there are many ways, actually. I guess one way would to be, like, let's say I have a constructor that returns a totally different type, like false. So that doesn't make sense. Of course, Haskell would tell you the same thing if you try to do a GADT that has this type. There's a positivity condition that has to be satisfied. So this is going to be a little bit confusing, but if I have something like this, so Coq rejects that because I could use a type like this to construct a term which essentially loops forever. And then I could prove all theorems. As far as how I would do that, I don't think maybe we can chat offline about how that would work. I can essentially encode the untyped lambda calculus as an inductive data type, and then define an evaluation function on it, if I were allowed to do something like this. So that would be very bad. Yes.
What we call conjunction here is the constructor.
Yeah. Yes.
And then in line 22, we are applying the constructor conjunction to true, true. Or how do you read this line?
Yes. So this, let me get to that in a second. Do you have a question?
A comment.
Yeah.
It might be worth pointing out that one of the reasons the standard library tends to heavily favor inductive definitions is because Coq's core logic is the calculus of inductive constructions. So it's in the inductive definition is the most primitive expression of these constructions in the logic of the core.
Yeah, that's great. And I think another possible reason is that when you do it this way, you get a nice induction principle generated for you automatically.
Right.
And that turns out to be really convenient for doing proofs by induction, as we will see. Maybe a brief word about the theoretical foundations of Coq. So just kind of build it up from, we have the simply typed lambda calculus, right? Which is just like, it's like you have basic simple types and arrow types, like functions. and there's no polymorphism or anything. It's like Go's type system. Like there's no generics. It's like it's funny to think about it that way. And then if you add polymorphism, you get system F, right? So that's the polymorphic lambda calculus. And if you add type operators or like type level functions, then you get system F omega. And then you might think, okay, that's like I've covered 3 of 4 possible situations in this what's so-called the lambda cube. And the other possibility would be if I have sort of like functions that take terms, like at the bottom level, and return types. And those are dependent types. And then Coq adds one more thing on top of that, which are inductive data types. So that's the calculus of inductive constructions. So that's what that was about. Cool. OK, so back to this thing. So I want to prove that true and true. I want to prove true and true, right? I should be able to prove that. It should be easy. Turns out to be kind of like a nasty looking term. But let me explain what's going on here. So if I look at this constructor conj for conjunction, it looks like it takes 2 arguments, right? It looks like it takes a proof of P and a proof of Q. 2 arguments. Secretly, they're actually, remember the whole inductive data type is actually parameterized by 2 propositions P and Q. So there are actually 4 arguments that I have to provide here. So I have to provide a proposition P, a proposition Q, a proof of P, and a proof of Q. And that's how I construct a conjunction. And so that's why here you see 4 arguments. So I'm calling the conjunction constructor. I'm giving it the 2 propositions that I want to prove, which are true and true. And then I'm giving it the 2 proofs of those propositions, trivial and trivial. So I have 4 arguments here. I would have liked to make maybe the propositions implicit, but it turns out you can't do that for legitimate reasons.
We infer the true from the trivial, or?
Yes, I would have liked to write just conj trivial, like not mention types anywhere, have them be like inferred. Sadly, that doesn't work. In a moment, actually, in a very small moment, I'm going to talk about Coq's like proof mode, which really helps you build up these terms using tactics, and that's how you want to do proofs. You don't want to write proofs like this because it'll take a long time. Yes.
Just to reiterate that, that's you passing 2 types and then 2 values to conj?
Exactly. Yes, I'm passing 2 types and then 2 values of those types. Yep. Cool. Any other questions about conjunction? Logical conjunction? It's just a data type. It has 1 constructor. You give it 2 proofs, then you've proven the conjunction. Yeah.
What is the difference between prop and set in practice?
In practice, not much. In theory, one thing to note is that I'll just say this without explaining too much, but prop is impredicative, and set is not. Set is predicative. I think that like Agda only has 1 of these like kinds, and it's just predicative, I think. So that's a theoretical difference between prop and set. In practice, there's not much difference except for the extraction mode in Coq will erase all the terms that have a type whose type is prop. So basically erase all the proofs. Yeah.
They're actually both predicative. The only difference between prop and set is the name. And as you said, the prop, anything in prop is not extracted.
Did that change in a recent version of Coq?
8.4.
Okay. Okay. Both predicative.
I'm sorry?
Are you sure that prop is predicative? Because
They're both predicative.
because or x and when it x is in prop, and also also prop.
I'm sorry?
Then you have or x, and then when x is in prop, or PQ, PMQ is in prop. And that means it's impredictable.
I don't think that's actually impredicativity. That's just polymorphism, right?
No, because
The way we-
when you have set and you try to do that, then it's in type. So it's 1 and above.
Oh, so if I change this definition to be in set,
It will fail because, yeah.
ah. So how do we reconcile this claim?
So you can construct impredicative definitions.
Yes,
That's true.
yeah.
Cool. for the rest of us, let's just like, yeah.
But back to the in practice question. In practice, the only difference is that prop is not extracted. Anything that's in prop is not extracted by extraction.
Okay.
Prop is logical content. Set is computational.
And what if you match it and the effects are run indicated?
Ah, yeah, that's a good question too. Yeah, so cock will prevent you from doing that. Actually, it can prevent you from. So, what you're about to see is a proof, and I've ended the proof in. This is a slightly related thing. I've ended the proof in this keyword QED, and that makes it an opaque definition, which means I actually can't look at what the proof is later on in the code. I'm not allowed to like extract information from it by pattern matching or whatever. However, if I end the proof with the keyword defined, then I can. Then it's what's called a transparent definition. So you sort of have some control over that. Okay, let's just talk about proof mode. Yeah.
Is this what you would say? That's the same thing as define.
I don't know what safe does. Like this?
Yeah.
It's a syntax error?
That's define, which allows you to speculate that thing.
Yes, yeah. So we just talked about define and QED. I don't know what save does. In my 2 years of using Coq, I've never needed save, so maybe you don't either. Okay. So we saw examples of giving proofs by just manually writing out the proof terms in Galena. And we saw that it's also quite nasty to do that. So this being like, I mean, this is like the easiest proof you could possibly do, almost, right? But it's already like, why do I have 4 arguments there? So much better to use a proof mode. So here what's going on is, I could actually replace this with definition. It's the same thing. Coq has a multitude of ways to write this. You could also write lemma. So it's up to your fancy, which keyword you want to use. But so I type the keyword theorem, and then I give a name to this theorem. And really what I'm doing is I'm just defining a variable that has a specific type. And the type is and true, true, which is corresponds to the proposition I'm trying to prove. So what proof mode is going to do is it's going to help me construct a proof of this type, or proof of this proposition. So okay, now let me just show you what's going on in the right-hand side. So I have one sub-goal. A goal is like that's something I have to prove. I have to prove that and true, true. So how am I going to prove that? So there's a tactic called apply. I think this is one of the most basic tactics. And basically what's going on here is, if we look at the type of conj, which is just a constructor that I've defined right here, the conclusion, or it's a constructor that has a return type, which matches the thing I'm trying to prove if you replace P and Q with true and true. So what apply does is it basically substitutes away this goal and replaces it with the premises of the conj constructor. So I'll have to prove P and Q after this. So I'm just gonna step to this. And by the way, to step through this proof, I'm using control up arrow and control down arrow in Coq IDE. If your key bindings might be different, or if you're using proof general, it'll be totally different. Okay, so I've written apply conj, which applies the conj constructor, and it has 2 arguments, right? So now I've got to prove those 2 arguments. That's what's going on. So I have 2 sub-goals, and I can focus the first sub-goal with a hyphen, like this. Some people don't use the hyphens, like they don't use the bullets. They just write like all their proofs like linear style like this, or maybe they use indentation as a convention. You can do that, but I like the bullets because if you have the wrong number of cases maybe, because let's say you're refactoring some proofs and you change a definition somewhere to have one more case or one fewer case, then Coq will complain that the number of bullets you have doesn't match the number of cases that you had in your inductive type. So it's like an extra way to catch. Well, it helps with error reporting, I guess. That's the only thing. All right, so I'm going to focus the first sub-goal, and now I have to prove true. But remember, true I can easily prove that because there's a constructor here that takes no arguments. So there's no obligations that I need to satisfy. So I'm just going to apply that constructor. Cool. So I'm done with that subgoal, and now I'll go to the second subgoal. And then I can do the same thing, because I'm just proving true again. So this is our first proof in proof mode. And now I think it's instructive to take a look at the actual proof that was generated from this process. So I'm just I just wrote like the script to generate the proof. But if I want to like look at the real proof term, I can see that it's actually the same as what I wrote before manually. It's exactly the same, right? So conj with these 4 mysterious arguments: true, true, trivial, trivial. OK. Now there's a shorter way to write this proof in proof mode, and there's this thing that is a semicolon, and this is called a tactical in the LTAC language of proof scripts. And what it does is, remember that when I apply this constructor, I get 2 subgoals, right? I have to prove true, and then I have to prove true again. But why do I have to write that proof twice? I might as well just apply this to both of those subgoals. So semicolon basically means if I have a tactic that generates a bunch of subgoals, then I'm going to apply the next tactic to all of them. So that's all that's happening here. It just makes the proof a little bit shorter. Yes?
So when you do that and you're applying it to all of the subgoals, if for say one of the subgoals that doesn't fit, will Coq just ignore it if there?
Ah, that's a great question. So it depends on the tactic. So some tactics will fail silently, which means that they just won't have any effect when you run them if they're not applicable. So an example of that maybe would be, I think if I type auto here. So auto is a very helpful tactic that we'll probably learn about later. But right now it doesn't do anything because it kind of just failed. But it failed in a graceful way. Not all tactics are like that. So for example, if I do something like this, OK, that one fails gracefully too. I don't know. Maybe. Oh, well, anyway, so basically a tactic, it's up to the author of the tactic to decide how it fails. And if you use this like semicolon tactical, and you have some tactics that fail hard, then the whole thing will fail, and you'll get stuck. So yeah, but actually there's a way you can do like try. You can do like this, or this maybe. And try is kind of like, I don't know, you probably have some intuition for this word, but it's like if it fails, then just do nothing. Yes?
You said that Coq has a few languages, right? There's like Galena and then this other one, right?
Yeah.
Are we using this other language now with this apply?
Yes, yeah. So the apply tactic is in the language LTAC, which is the language of, basically the code that you write in between the keyword proof and QED is LTAC.
Okay.
Yeah, and this LTAC is constructing a term in Galena, the other language. So Galena is like the core strongly typed calculus with dependent types, and all your proofs end up in Galena eventually. That's a great question. OK, any other questions about true and true? Yeah.
The other languages for defining tactic. Is there only one language?
Say that again, I'm sorry.
Is this the only language for LTAC, the only language for defining tactics?
Ah.
Are there others?
Well, actually, you can define tactics in OCaml as well. And many of the built-in tactics are defined that way. So I think you have 2 options available, basically. The LTAC scripting language and then OCaml.
Could any kind of language be hard?
Well, I think you'd have to just modify. You'd have to recompile Coq with some extension. Yeah. All right. People are getting bored. I'm leaving. OK. Oh, really?
In 2 minutes, yeah.
Oh, wow. I thought we had another half hour. Oh, wow. OK. OK, well, you can imagine defining the rest of the logical operators this way. So for example, I can define OR, which has 2 constructors. I can define if and only if like this. And then from that, you basically just compose these things to build larger and larger proofs. Did I miss something?
No, we were hoping that maybe it would keep going.
Ah.
Have nothing else.
Oh, everybody wants more. You got to leave them wanting more.
Because I think Sandy's in here next.
Ah, OK.
Take it to the encode.
The encode? OK. Cool. Well, if anyone wants to learn more about Coq, you can follow me. Well, thanks for coming. Great.